Okay, so good afternoon, everybody. I'm really happy that I can see you in such a big numbers. I would like to welcome you at now we are at a game changer stage, but actually this the next talk or performance is prepared together also with the Big Bang stage. And I will be very short in the introduction, and I'm really happy that today I can introduce you two very important people from the biggest and the most important laboratory of particle physics from CERN. There is now the reason actually why we have this opportunity to welcome here those two persons is that right now in Prague there is the biggest conference in particle physics called ICHEP. And in parallel, we are also celebrating 70 years of existence of the CERN. So now let me introduce Fabiola Gianotti, who is Fabiola is now the Director General of CERN, but I met her for the first time when she was actually the head of the Atlas experiment. And the second person that will be, sharing with us, the details about the CERN and everything is Charlotte Warakaul, who is the Director of the International Affairs in CERN. So thank you both for coming to Ostrava.
Thank you very much, Martin, and good afternoon. We are very, very pleased to be here tonight and to present one of the most fascinating scientific adventures of humanity, namely research at CERN. In particular, we are going to talk about the Higgs boson, a minuscule and very intriguing particle, and its role in the evolution of the universe, from its birth to the future, and also its role, its impact on our life. So let me remind you that CERN is the biggest laboratory in the world for particle physics, and particle physics is the most fundamental of all sciences because it studies the smallest constituents of matter and the universe. Smallest constituents, we call them elementary particles, means particles that cannot be cut into smaller pieces. So they are really the building blocks of everything we see on planet Earth in the visible universe. And particle physics also study the most fundamental laws of physics, the laws of physics at the most fundamental level. So these nice photographs show the region of near Geneva in France. So here in red you can see the border between Switzerland. Here you see here Lake Geneva, Geneva Airport, Switzerland, and here in France. And here you see this circle shows the position of the Large Hadron Collider, which is the most powerful accelerator ever built by humanity. It's a 27-kilometer ring, 100-meter underground, and I will come back to this later on. So CERN missions is based on 4 pillars: research, technology, collaboration, and education and training. And I will cover the first 2 items, and then Charlotte will cover collaboration, education, and training. So let's start with research. What we do at CERN, as I said, is to study the smallest constituent of matter. So what are these smallest constituents? We all know that matter is made of atoms. This I think everybody knows. Atoms are made of a nucleus surrounded by electrons. The nucleus is not elementary, is made of protons and neutrons, and protons and neutrons in turn are made of substructure called the quarks. And as far as we know today, quarks and electrons are elementary particles. They cannot be cut into smaller pieces, so they are the fundamental constituents of the ordinary matter we know. So all of us, this room, this table and chairs, everything, even the president of the Czech Republic, is made of electrons and quarks. So the Large Hadron Collider at CERN allows us to study matter at the level of the quarks. So on physical scales, how large or big are the quarks? Physical scales are smaller than a billion of a meter. So this big accelerator can be seen as, imagine, as big microscopes. If you want to study a human cell, you use a small microscope in a lab, but if you want to study much smaller structures like the quarks on physical scales of the billions of a meter, you need much more energy in order to have a much higher resolution power, and so you need a big accelerator. At the same time, the study of the very, very small allows us to understand the very, very big, so the structure and evolution of the universe. This is because we know today that the universe had origin some 13.8 billion years ago, following a big explosion called the Big Bang. At the beginning, it was very hot, like an explosion, very hot and very dense, and it was a gas of free elementary particles. So that's why, by studying the elementary particles in the lab, in controlled conditions, we can understand what happened in the very early universe. And then with time, it expanded and cooled down, and through cooling then, these elementary particles combined with each other. So first the quarks to form neutrons and protons, then neutrons and protons to form nuclei, nuclei with electrons to form atoms. So essentially this cartoon on the opposite direction, up to the beautiful things that we see today, stars, galaxies, planets, etc. And there are two complementary ways to study the universe and its evolution, its history. One is to use telescopes in space or on Earth, and telescopes look at the big objects, so stars, galaxies, etc., and by studying the farthest object, they can go back in time, because the universe is expanding. So if you look at the farthest object, you can go back in time. But they cannot go back to the very, very initial instance of the universe. And this can be done by using accelerator. With the LHC, the Large Hadron Collider, that I mentioned before and I will show later on, with the Large Hadron Collider, we are able to probe the universe as it was millions of a second after the Big Bang, 10 to the minus 12 seconds after the Big Bang. This means that when we collide our beams after accelerating them and smashing them, the energy that we produce in the collision corresponds to the temperature that the universe had at that time. And this temperature is 100,000 billion times the temperature in this room. So we produce this very, very high energy, which corresponds to the temperature of the initial universe, and then we can study in the lab the same phenomena that have characterized the universe when it was a little baby. So to do this, we need three main instruments. We need particle accelerators, we need particle detectors, and we need big computing infrastructure. And we need to develop cutting-edge technologies in many domains, from superconducting materials and magnets to fast electronics, from big data to quantum computing, from cryogenics to vacuum techniques, etc., that then we transfer to society at no cost, for free. So I will come back on this later on. So the Large Hadron Collider is the most ambitious and most powerful accelerator, and with its detectors and computing, the most powerful project in particle physics ever. So as I said, it's a 27-kilometer ring, 100 meter underground, and what we do is to accelerate two beams of protons in the two opposite directions of the ring. We accelerate them up to the highest achievable energies, where the limit only comes from technology, and then we smash them at these highest possible energies at 4 points of the ring, where in 4 big underground caverns we have installed 4 big instruments. They're called particle detectors. Their names are ALICE, ATLAS, CMS, and LHCb. And their goal is to say they surround the full solid angle around the collision point, And their task is to detect all the thousands of particles which are produced in the collision, and so to give us a picture of the collision event. So operation started in 2010. With this accelerator, we were able to bring leadership in at the energy frontier, as we call it, to Europe from the United States. And 2 years later, Atlas and CMS, the two biggest experiments, announced the discovery of a new and a very special particle, so the Higgs boson. And I would like to stress that the Czech Republic, through its institution and university, has contributed in a very important way to the LHC experiments and the computing, and so then we'll see later on the role of the Czech scientists. So this is a spectacular image of the LHC underground tunnel, the 27-kilometer tunnel. The single most important component of the accelerator that has allowed us to make a big step in energy compared to the previous collider, previous accelerator, which was in the United States, is an ensemble of 1,232 high-tech superconducting magnets. Magnets are used to keep the protons on the circular trajectory and then to bring them into collision. So this is the dominant technology, and these magnets have been developed at CERN, which has built the prototype. The technology was not known to industry when we started to work on these magnets, so we built the prototypes in-house, and then we transferred the technology to industry, to 3 leading industries in Europe, and so it's a very good example of collaboration between fundamental research and industry. The detectors are also quite impressive. You can see this is Atlas. You can see the size of 2 average human beings. You see it's the size of Atlas is half the Notre Dame Cathedral in Paris, underground. The other experiment, CMS, weighs more than the Eiffel Tower, so you see it's a big experiment, but at the same time, they are extremely precise. They are made of 100 millions, for instance. The core of the experiment is made of 100 million of silicon detectors with very, very high, with very, very low, very small size in order to reconstruct the collision. So how do we reconstruct the collision? So you see a cartoon here, actually an event display. Here we have a one beam coming from the Large Hadron Collider, the other one, proton beams. They collide here. They produce a burst of firework of particles, and these particles traverse the detector, and the detector is made of several layers which are able to not only reconstruct the trajectory of each particle, but also to measure the energy and to identify the particle. So essentially these detectors can be seen as giant 3-dimensional cameras that take pictures of the collision event. However, they are very, very challenging because the 2 beams of protons collide 40 million times a second. So they must be extremely fast. We do not store and we not record all of this picture, all of this collision, because there will not be enough computing capacity, but typically thousands of them are selected. Computing is the other important component. So for the Large Hadron Collider, given the huge amount of data that the experiments were going to record and the huge number of processing, large amount of processing power required, we have developed a new model. It's called the Worldwide LHC Computing Grid. It's a grid of 170 data centers spread across the world, which altogether offers a total storage of 2,000 petabytes of data. This is a huge amount of data, and something like 1 million processing cores. And actually, grid computing has been the precursor of cloud computing. So it prepared the road to the cloud. And the Czech Republic has a high-performance center in Prague. So here are a few more key figures. So when the accelerator works at full speed, like now, every beams contain 200,000 billion protons, which make 11,000 revolutions of the 27-kilometer ring per second, because they travel very close to the speed of light, and the energy stored in each beam is enormous. 400 megajoule corresponds to an Airbus at full speed. So clearly, this also tells you how well we have to control the trajectory of the beam, because you have to make sure that it does not destroy the magnets and the rest of the accelerator component through which it's traveling. So a few words about the Higgs boson, a very special particle, still mysterious. The Higgs boson is very important because it is related to the mechanism that allowed matter to form in the early universe. 10 to the minus 12 seconds after the Big Bang, atoms were able to form in some sense. And so this is the matter we are all made of. And so without the Higgs field and the Higgs boson, we will simply be not here. We will simply not be here. So the first link between the Higgs boson and our life is that without the Higgs boson, we will not be here. So the Higgs boson is clearly related to the first instance of the universe and its evolution. It may also be related to its fate, because based on what we know today about the mass of the Higgs boson or the mass of other particles, the universe will not be in a stable situation. We will be in what we call a metastable state. So the lowest energy state is not the one we are today. So one day the universe could transit, could decay to the lowest state. Maybe not tomorrow, so we are maybe safe, but one day this may happen. So that's why also studying the Higgs boson is very important to understand the fate of the universe. So how do we see a Higgs boson in the ATLAS and CMS detector? The Higgs boson, once produced, I mean, it has a very short lifetime, 10 to the minus 26 seconds. So once produced, it disintegrates itself immediately into other particles. For instance, into 2 photons. Photons are very well-known particles. This room is full of photons. Photons are the quanta of light. Or also, as you can see here in this picture, the Higgs boson has been produced here in the middle, and it disintegrates itself into 4 electrons, and what we reconstruct in the detector are the tracks of the 4 electrons. And then by looking at the energy of the electrons, we can reconstruct the mass of the mother particle. And when you do this on many, many collisions, then you see a nice peak corresponding to the mass of the Higgs boson, 125 GeV, which is more or less 130 times the mass of a proton. So this is the signal of the Higgs boson in the ATLAS detector, and this is a Higgs boson in CMS. So particle physics today has accomplished a lot. We have understood what the building blocks of the visible universe are and how they interact at the most fundamental level. All the elementary particles that are predicted by the theory that describes the visible universe is called the Standard Model, have been discovered and measured. You can see they are made of different types of particles. The Higgs boson is special. It's in the middle because it does not have the features of the other particles. Mainly the fundamental particles are made of quarks and leptons. As we said, the quarks are the fundamental constituent of atoms, like the electrons. So the first family here, up quarks, down quarks, and electrons, made all of us. And then of other particles that at the microscopic quantum level are responsible for transmitting the fundamental forces. So at the microscopic level, 2 electrons interact electromagnetically through the electromagnetic force we are all familiar with by exchanging a photon. And similarly, the weak force, which is responsible of the thermonuclear reaction in the sun, is transmitted by exchanging the Z and W particle, and the strong force which keeps nuclei together through the exchange of gluons. So these are the particles you can see on my t-shirt. They are really, okay? Now the problem is that although we understand very well how the visible universe works, still there are a lot of open questions. One is the dark universe. So I said before that we are made of the ordinary matter that you also see in star, galaxies, etc. However, this ordinary matter is only 5% of the universe. Meaning that when you look at the sky and you see star, galaxies, etc., what you see is only 5% of what is out there. All the rest, 95%, is unknown, made of forms of matter and energy that we do not know and do not interact with our instruments, and so we call them dark matter and dark energy. 95% of the universe today is dark to us. We infer the existence of dark matter and dark energy indirectly from other proofs. And now these proofs are extremely compelling. So 95% of the universe being unknown, of course, is a bit of embarrassing for us scientists, but at the same time is also intriguing, so there is still a lot to understand. We don't understand why the elementary particles are organized in families in this way. There is something bizarre in this. We don't understand, for instance, why our universe is only made of matter with very little antimatter. Antimatter, to oversimplify it, is matter with the opposite sign. So an electron, as you know, is a particle with a negative charge. The antiparticle of the electron has the same characteristic, except that it got a positive charge. So we think that at the moment of the Big Bang, at the time of the Big Bang, matter and antimatter were produced in similar proportion, and then something happened in the early universe and antimatter disappeared. We don't know where it went. And today's universe is almost exclusively made of matter. Thank goodness, because matter and antimatter have the bad feature, and when interact, they get close to each other, they annihilate into energy, photons. Okay, so if I take an electron and anti-electron, if they interact, then they disappear into two photons. So we will not be here. So that's also interesting for our life. However, we don't understand how this happened. So this question requires physics that goes beyond what we know today, what we call new physics. There must be phenomena, there must be laws, there must be new particles that can explain this open question, like dark matter, antimatter, dark energy, etc. And so at CERN we are already thinking of the successor of the Large Hadron Collider. The best candidate today is what we call a Future Circular Collider, for which we are doing a feasibility study, so it's not yet approved, but we are working on its feasibility. So here you see the Large Hadron Collider, 27 kilometers, and then the trace of the Future Circular Collider, if it will be built, 90-kilometer ring with new technology, which will allow us to make a jump by a factor of 7 in energy, and so have more opportunities to address the open question with with a possibility of answering. There is a similar project that is being proposed in China, so there is a little bit of competition at the moment between Europe and China if you want to keep leadership in this physics in Europe and the technologies that go with them. We should really go ahead with this project. CERN is not just the collider, the Large Hadron Collider. We have a very broad physics program. We have, for instance, a facility which studies nuclear physics facilities, which produces radioisotopes to study nuclear physics, but also for medical application. We have the only dedicated antimatter facility in the world. I said that antimatter does not exist in the universe. There's very little antimatter in the universe, but we can produce it artificially by sending a beam on a target. We produce many particles and many antiparticles, and then study them and compare matter and antimatter to see if there is any little difference that may explain why the universe does not have any antimatter. We have an experiment cloud to study the impact of cosmic rays on climate change, and so on and so forth. So I move now very briefly to the next topic, which is just a couple of slides. So you have seen that at CERN we build extremely complex, big, ultra-precise instruments, without which we will not be able to accomplish our objectives. And I said that we need to develop cutting-edge technologies in many domains. And these technologies are transferred to society and have a huge impact on our life. And this is the second link between the Higgs boson and our life. In order to discover the Higgs boson, we had to develop technologies that now today save millions of life, for instance, by using accelerator to treat cancer. Maybe the most famous example, for sure, is the World Wide Web, which was developed in 1989 at CERN, when Tim Berners-Lee was a CERN employee, and then made available to society 4 years later at no cost, because the CERN founding convention established that whatever we find in terms of scientific results, technological developments, etc., must be made available to humanity at zero cost, no cost. Another example, as I said, is accelerator to treat cancer by using protons or light ions like carbon ions or electrons, which have the nice feature compared to the more standard X-ray therapy, that they are very focused. X-rays spread over everywhere. So if you bombard the tumor with X-rays, you bombard the tumor, but also the healthy tissues around it. With protons, with light ions, with electrons, you can be much more focused and only hit the tumor. So there are therapy centers in Europe which use accelerator built at CERN. Here you can see a very nice scanner of the wrist. You see the precision, three-dimensional scanner, color, with extremely high resolution produced with CERN electronics, and this picture went on the New York Times. We develop a lot of superconducting materials, also cables, which are able to transport huge amount of current. We are talking about thousands of ampere without losses, and so this potentially has a huge impact on society, because we live in a world where we need to be sustainable. So of course, if you are able to transport electricity with no losses and with very, very small cables, this of course has an advantage for society. And we have today collaboration with Airbus, which wants to implement clean air transportation, and so they are interested in our cables. You see here an instrument, a dosimeter, which is an instrument to monitor the radiation on board of the International Space Station. This is a CERN instrument. And machine learning techniques of CERN are used for autonomous car driving, and we have a collaboration with Volvo. So these are just examples of the impact of the search for the Higgs boson, the impact of the fundamental research we do at CERN on our life. And now, I now leave the floor to Charlotte.
Thank you so much for setting the stage so beautifully for what I will talk about, because I will talk about how all of this incredible science and these technology developments have been made possible, and that is through global collaboration amongst scientists. And I think this is a fantastic story to tell here, where the motto of the melting pot is ideas without borders, and this is very much about science without borders. And in order to understand how this collaboration has come about and how it has evolved and why it's so impactful, we also need to travel back in time. Maybe not 13.8 billion years, but we need to travel back to just after the Second World War, where there was a coalition of visionary scientists and politicians that came together to develop the concept of how to take forward peaceful collaboration in science. And there were really three main objectives at the time. First and foremost, to restore scientific excellence in Europe, in the ashes after the Second World War, and also to reverse and to mitigate the brain drain that was taking place at the time, in particular to the US. There was also a focus on fundamental research at a scale beyond the capacity of any single nation. You have seen the size of the collaboration of the instruments at CERN. This is not possible for any one country or any one community to do by themselves. And the politicians and scientists at the time also saw science as a way to glue together a continent that had been at war only a few years earlier. And you see here some of the founders, and I have to immediately say that there's not a great deal of diversity here. This has changed over time. And these ideas coalesced already in the 1940s, so it's very early after the Second World War. And under the patronage of UNESCO, which is the UN Organization for Education, Science and Communication, this came together as the CERN Convention, which was established in the early 1950s by 12 founding member states at the time. And this convention was ratified by the 12 states, and on the 29th of September 1954, CERN was born. This is when the convention entered into force. And this is really the start of an incredible scientific adventure and 70 years of scientific achievement. Now, Fast forward 70 years, what does that vision look like today? And you can see here that the initial 12 member states has grown to 23 member states today. We're extremely proud that Czechia is part of the 23 member states, joining initially in 92 as part of Czechoslovakia and as an independent state in 1993. We have a number of states that are in the process of joining the organization, so the membership is growing. Estonia has just ratified the convention, and they will become later this year the 24th member state of the organization. And if you look, it's very interesting to look at also our associate member states that are participating in the CERN family, but at a slightly different way than the member states. And you can see that this is really a global endeavor. India, Pakistan, for example, outside of Europe. Brazil has joined very recently as the first associate member state in Latin America. Chile is just behind. So there's a lot of growth also in Latin America and a lot of interest in the organization and in particle physics. We have a number of observers. These are organizations or states that have a particularly close relationship with CERN and have been part of the history and the scientific endeavor. But I also want to point out here the cooperation agreements we have with a number of non-member states. And many of these are countries that you would not necessarily associate with fundamental research, because CERN also has a mission to build capacity in countries that have developing communities in particle physics. And this allows them also to contribute and to develop and to benefit from what fundamental science brings. The organization has about 3,500 employees that are paid by CERN itself. And then we have, and I want to highlight this, an incredibly vibrant community of scientific users, about 12 to 13,000 that come from all over the world. They're not employed by CERN, but they're employed by universities and institutes in our member states and many others. And we have many of those who are working in Czechia with us here today. So if we dig a little bit deeper into this community, you can really see how diverse it is. About half of the scientific users at CERN come from our member states, a good proportion also from our associate member states. And then I want to highlight here also the large community we have from the US. And just to remind that one of the objectives of the founders of CERN was exactly to reverse the brain drain. And you can see that they have very much succeeded, because CERN is today one of the largest laboratories for particle physics, also for the US. Interestingly enough, you see also here that about 10% of our user community come from our non-member states, and this is also a way to show that there's really growth in this community. Many countries are looking to build and to foster particle physics, also to be able to benefit from what that brings on many levels. A couple of numbers for the Czech Republic, which has an extremely rich and diverse community. I'll talk a little bit more about what our Czech colleagues are doing with CERN. You see here that the community is 252 researchers from institutes and universities in the Czech Republic, and that is a very, very large number when you compare to other countries of the same size, which really speaks to the very deep tradition for physics and for fundamental research in the Czech Republic. Now, I think it's interesting to look a little bit at how this has evolved over time. You see here a graph of the evolution in the number of users at CERN over the past 20 years. And you see here that the community has actually doubled in just 20 years, which is really impressive. And this is very much as a function of the projects, the scientific program at CERN, which attracts an increasing number of users because of the level of ambition and the attractiveness of the infrastructure. And as we look to the future, and Fabiola already highlighted that there are ambitious plans also for the future, it's important to keep this community together and also to continue to grow it for the future. Now, CERN is a very unique model of collaboration that has evolved, that has been fine-tuned over time, and it is also a model that has inspired much beyond particle physics. Fabiola spoke about the large the LHC experiments that are themselves models of collaboration, also competition amongst scientists. And these are actually being studied also by sociologists and others to understand how this very flat and very inclusive model of collaboration can be so successful in delivering on the scientific objectives of the organization. It is also a model of collaboration that has inspired others to create new organizations, new laboratories built around the ideas that are at the heart of the CERN model of collaboration. You see here Sesame, which is a very unique infrastructure which is based in Alan, just outside of Amman in Jordan, which is a synchrotron light source that brings together a number of countries in the Middle East, many of them not necessarily the best of friends, but scientists from these countries work together in the region, and they use also science as a glue to see to how they can build bridges amongst their communities. CERN is also working very actively with other intergovernmental organizations, for example, the United Nations system, which is a big partner of ours. We, for example, provide also IT infrastructure for satellite imaging that is used in the UN system, for example, for emergency responses. And these are all models of collaboration that allow the organization's impact to go much beyond the organization itself. We work very much also on a global level in order to see how our experience in science collaboration can inspire others. We have observer status with the United Nations. We're the only big scientific organization that have that. And we're working very closely with many parts of the UN system and others in order to promote the Sustainable Development Goals. We have done a mapping of all the goals that we are already contributing to, and we're trying to target many of the activities that we have, particularly when it comes to knowledge transfer that Fabiola already spoke about, in order to see how we can advance the goals. And this is also a way that the research on the Higgs boson has a very direct impact on many people's lives, for example, through technology development that benefits health, educational programs also to promote gender equality, particularly in science, energy management, innovation, and also, of course, international collaboration and inclusive societies that are goals 16 and 17 of the SDGs. Now, when it comes to impact on society and how fundamental research really is a driver of socioeconomic development, one of the biggest factors here is the impact that we have through people, through young people that are trained and educated and also inspired to pursue careers in STEM. And if we look a little bit here, it's quite interesting to look at the age distribution of the scientists working at CERN. We see here a peak at 27. It's not just Fabiola and myself, obviously we are quite important there. But this is because at any one point in time, we have about 4,500 people in different stages of education and training at CERN. I have to say we're also very encouraged that it continues. We need to increase this graph. We have a Director General who's still very active and who just turned 100, so clearly also particle physics is very good for the health because you continue for a very, very long time. But you can also see that even if the peak is here, they don't all stay in the field. And this is because the field of particle physics cannot necessarily absorb all of the PhDs, for example, that come out. Many of them go into other industries. They bring the skills and the ways of collaborating with them and have an impact on society. You see many of them go into industry. IT, for example, is a big area here, but also into government and other areas of research. And they bring with them an incredible capacity to be a force for good in other parts of society. So we're working in a very dedicated way in order to encourage, to inspire young people to take up a career in science. It could be particle physics, but also other sciences. So we have, apart from the dedicated programs we have also within the experiments, we have programs, competitions for high school students. We have programs for high school teachers. We have about 1,000 teachers that come on site every year and get new skills. They learn how to teach particle physics in the classroom and to inspire the young people that they're working with. We're also working in a dedicated way to reach out. We're very visible on social media in order to be able to engage with and to encourage the next generation to take up careers within STEM. And you can see some of the numbers here for the Czech Republic, which is an area, which is a country that has a very active outreach and a very active profile when it comes to educational programs, also for young people. The latest activity we have in this area is the CERN Science Gateway, which is our new Center for Science Education and Science Outreach. This is a very unique facility that just opened in October of last year, all constructed for money outside of the CERN budget with philanthropic donations. And we have really three objectives for the center. First of all, to share the wonder of science, the beauty of science with all the visitors who come, but also to encourage, to inspire young people to join sciences. And we want to also engage and build bridges to society to increase the trust in science, because science is really at the heart of addressing all of the challenges that we face today. So we have a number of educational programs. We now have educational programs from age 5 and up. We like to say from age 5 to 105 plus, because we're very ambitious through science shows, lab workshops, also for the youngest. But we also want to share beyond the infrastructure itself, so we're building programs that also have an online profile in order to share what happens at Science Gateway, also on a much wider scale. And you can see we get many different visitors, including the French president. And much as he was much encouraged by Fabiola to get stuck into the hands-on experiments, you can see that the kids are a little bit more adventurous. So I think he'll have to come back in order to really get into the experiments. I'll just conclude with a couple of words about the very special relationship that there is between CERN and the Czech Republic as a very integral part of the CERN family. As I already mentioned, the Czech Republic has been with us for a long time, first as a member state, 92 with Czechoslovakia, and then as an independent state in 93. And you can see that there is a very large number of institutions in Czechia working closely with us. And Czech scientists, and you saw that there's a very large number of them, are involved across the CERN scientific program with a very important contribution to the LHC experiment, but also to the fixed target experiments. This is what was mentioned earlier, the scientific diversity program, which is very important at CERN. Very important profile also when it comes to computing. We already mentioned the tier 1 center, tier 2 center? Tier 2 center in Prague, but there's also high performance computing here in Ostrava. So this is really an incredibly vast portfolio when it comes to the scientific program. Industry in the Czech Republic is also very strong and has provided important contributions from the high-tech sector, from the industrial sector, and the industrial return to the Czech Republic is actually very impressive, and I think the envy of many other member states. So we're extremely proud and pleased to have such an incredibly close relationship to the Czech Republic. Now, this was just a few words about collaboration and how we take that forward. How is it that it's possible to bring science to the level that we have brought science to? But it doesn't stop there. I think we want to talk a little bit about the future, and I hand over to you.
This is our last slide. I wanted to conclude with a beautiful image of the sky, which was taken by the James Webb Space Telescope. You remember it was launched Christmas 2-3 years ago. NASA, ESA, the Canadian Space Agency. And when you look at such images of the sky, of course, we are all fascinated by the luminous objects. You see the galaxies, the stars, they are so beautiful. But for us, particle physics, like for astroparticle physicists, cosmologists, astronomers, what really capture our eyes is the dark. For me, when I look at that image, I see the dark and the empty space, because we have already discussed the dark universe, we don't understand it, so for me it's the most fascinating thing. But also the concept of vacuum. The vacuum is not empty in physics. The vacuum is full of energy. The energy of the vacuum is most likely responsible for the current accelerated expansion of the universe. The vacuum is full of particles flashing in and out. We don't understand this structure, so the next frontier in particle physics, astroparticle cosmology is to understand the darkness and the vacuum. Thank you.
So I would like to really thank you, both of you, for giving this highlight of what we know and what we don't know about our universe at the microscopic level, and also at these big scales, and also for the role of the CERN, just beyond actually the fundamental science. And we have now quite big room, I think, for questions from you, from the audience. So you can ask in English, or you can also ask in Czech, and I will just translate it. So are there any questions now? And don't be shy. Okay, so let's start over there. And just please wait for the microphone.
I would like to ask you, you said that mostly research in CERN is about taking 2 or more protons and make them crash in very high speed to each other. But how do you get into the collar? How do you separate them from the atom? Are they stable, or how does it work? Thank you.
You're asking how do we produce the proton beams? So the proton is the nucleus of the lightest and most simple chemical element, hydrogen. And the hydrogen atom is made of a nucleus made of 1 proton, nothing else, and an electron, 1 electron, okay? So we take a bottle of hydrogen, we separate electrostatically the proton from the electron, and then we take the protons, we inject them. Of course, it's much more complicated than what I'm saying, also because the accelerator complex at CERN is not just made of the Large Hadron Collider. There are several accelerators upstream, which are called the injectors, that are used to accelerate the protons in stages to prepare the beams, to give them the right time structure, and then they are injected into the Large Hadron Collider in the 2 opposite directions, and then finally accelerated up to the flat top energy, and then brought into collision. So it's a bottle of hydrogen.
Okay, I think there was a question over here.
Good evening. I wanted to ask about the energy of the vacuum, about the history and how it started, the discovery of it.
It started with quantum mechanics, essentially, when, of course, people realized, first of all, that there are virtual particles that pop up and out and in and out, that these virtual particles produce energy. They understood that the various fields that we know, the electromagnetic field, the Higgs field, contribute to the energy of the vacuum. And also, it was discovered a few years ago, in the mid-90s, that the universe is expanding at an accelerated speed, which was a total surprise, because you would expect that after the explosion and after the expansion, afterwards the gravitational force of the various masses of the universe will make the universe implode. And actually, no, the universe is expanding, so it means that every point in the universe runs away from every other point at an accelerated speed. And so there must be a force, we think it's a pressure, so that counterbalance gravity. We don't know the details, also because our prediction of the energy of the vacuum does not correspond to what we see, what we measure, what we see with the expansion of the universe. So it's a question mark, but it's a very interesting, how to say, casse-tête, you will say in French, something that you have to think of, experimentally and theoretically.
Okay, there is a question over there.
Hello, thank you so much for an amazing lecture. I would like to ask about the time schedule of the understanding the antimatter. When we can expect to understand dark matter and antimatter, like tomorrow in 100 years? What's the time schedule? Thank you.
If I knew, but the answer is that I don't know. These are big, big, big questions. The question of dark matter, for instance, is not a question that can be, like most of the questions I showed, can be addressed. I mean, we don't know what is the best instrument to address it, because it depends on the mass of the dark matter particles. If they are relatively heavy particles, they can be produced at the Large Hadron Collider or at the future collider. So colliders are the best way. If they are extremely light, maybe colliders are not the best thing. There are other approaches. So it's maybe not tomorrow, maybe not in 100 years, maybe in between, I hope. I hope they will still come within my lifetime. It would be good to know, to see our knowledge of the universe to increase from 5% today to 30%, because dark matter is 25% of it. So it's very difficult to tell when. But I think what is important is that we try to deploy all the experimental approaches that the field of particle physics and astroparticle physics has developed over the decades, and the technologies that allow us now to improve our, and to, how to say, to make our searches more powerful and more effective. So the technology has been very, very important, technological developments. So, and to use all these technologies and experimental approaches to try and tackle the problem.
Okay, another question. Okay.
Thank you very much. It's super interesting what you're saying. I would have two questions. The first one, you just said, so that's 25% is dark matter, 5% is normal matter. What is the rest?
Dark energy.
Dark energy, okay.
So the expansion of the universe.
And the second question, I'm a layman in physics, so it may sound stupid, but did the discovery of Higgs boson play any role in, or for quantum physics? What is the relation between that and quantum?
Yes, of course. So first of all, the Higgs boson is an elementary particle. It's itself governed by quantum mechanics. The Higgs field, which is associated to the Higgs boson, I didn't go into the details because it would have been a little bit heavy, but contributes, for instance, to the energy of the vacuum. And the Higgs boson, as I said, is a very special particle because you see that here, it's in the middle. And it's completely different from the other particles in terms of features, what we call quantum numbers in particle physics. It almost got no feature at all. It just got mass. Other particles have other features like the spin and many other things, but it just got mass. It brings a new type of force. It's not one of the forces that we know. You know, there are 4 forces: gravity, electromagnetic, weak, and strong. The Higgs boson brings another type of force called Yukawa force. And as I said, is related to the first instant of the universe, when 10 to the minus 12 seconds after the Big Bang, this Higgs field self-established in the early universe. Before the Higgs field, there was nothing. The universe was empty. There were just particles traveling at the speed of light, everyone, including electrons, quarks, like the photon. And then this Higgs field, through what we call a phase transition, installed itself, self-established in the universe, and the particles interacting with the Higgs field acquire a mass. So electrons and quarks became massive, and this allowed them to form atoms. If they were remain massless, atoms will not exist. We will not be here. So it's thanks to the Higgs mechanism, the Higgs field, and the Higgs boson is the manifestation of the Higgs field. So it's a very special particle, maybe also related to the fate of the universe. So and it's amazing that we have discovered it at CERN and that we have to do with it every day, you know, because we observe Higgs boson every day, and so.
I really like how physicists can use the T-shirts, you know, to explain, you know, all the particles, because Fabiola has the graphical representation of the standard model, and Charles has the mathematical representation of the standard model. So, yeah, I mean.
The visible universe is, at the quantum level, is described by just 4 lines. Those 4 lines describe everything: the elementary particles, their interactions, and the Higgs boson. The Higgs boson is this, just the last line here. Okay.
Okay, next question. Be faster.
Hi, thank you for the talk. I would like to ask about the future of the particle colliders. So you mentioned that right now you get in consideration FCC, and I remember when this consideration was announced, there was some critique about, like, it's quite financially intense project, and I would like to ask, like, some people are saying that maybe if they invest this money into more efficient accelerators, or the research would go different way for particle physics, it would be more efficient. So what do you think about these opinions?
So it's a very good question, and we are investing money also in new accelerator technologies. The FCC itself, for instance, will require new generation superconducting magnets with great impact on society. So, and we are also developing new accelerator technology like plasma wave field and others. But all in all, if you look at the various collider projects that have been proposed until now, the Future Circular Collider is the one that overall provides the largest physics output and the highest physics potential. So the European particle physics community already in 2020 recommended that we do a feasibility study for the Future Circular Collider. There are other approaches to understand to try and address the open question. As I said before, there is no single instrument that can give you the guarantee that all those questions will be answered in some time. But colliders are absolutely essential. I said that the Higgs boson is one of the most mysterious components of fundamental physics today. And the Higgs boson can only be produced at colliders. There are no other ways. So colliders are not the only instrument, but are a part of an essential program to address the open question. So we should continue.
Thank you.
Hello, I have a related question to this. FCC or future colliders. You have mentioned in your lecture that we need a new physics. What is the physical community expectation that these new colliders will bring them as discoveries? Will we be able to build this new physics based on their experiments, or how you see it?
So, first of all, maybe I should go back to one of my slides, and I didn't go into the details because it was a little bit complicated. Well, actually, Charlotte, please, can you show your T-shirt again? So this equation describes the standard model. I mentioned the special role of the Higgs boson, but there is another important thing. If you look at the standard model, we understand it very well. But the terms that where we have question marks are all the terms where the Higgs boson, indicated here with 5, sorry Charlotte, I don't want to touch you because indicated here with 5 is the Higgs boson. All these terms which involve the Higgs boson today are not understood. We don't understand the structure of the vacuum, we don't understand the mass of the Higgs boson, and we don't understand the way the Higgs boson interacts with the other particles so that we have this different family of particles. So all the things that we don't understand today in the theory that describe the elementary particles and their interaction are related to the Higgs boson. So the Higgs boson is a very powerful discovery tool. So there is one certainty in the exploration at the current collider, the LHC, which is now being made more powerful with an upgrade, and then beyond the LHC with the Future Circular Collider, which is measuring and understanding the Higgs boson with very high precision to try to solve all these mysteries. And this is a fact. The Higgs boson is there, so it's a fact. Concerning new particles that could explain dark matter, concerning how to solve the problem of matter-antimatter, we don't know if the Future Collider will allow us to answer your question those questions, because we are exploring uncharted and unknown territory. So, and this is the essence of research. If you knew what you are going to discover, then it will not be research. Okay, so for sure the Higgs boson program is something that we will have to do and use this Higgs boson as a discovery tool. But we know that every time we make a big jump in energy, every time we build more powerful instruments, those instruments and those increased capabilities allow us to make important step forward in understanding fundamental physics. The FCC will be the most extraordinary instrument to study physics at the smallest scales. And we know also from recent theory over the past 50, 100 years that physics at the smallest scales, the quarks and the smallest particles, is related to physics on the cosmic scales, so space-time, gravity, etc. So we are really going to probe the fundamentals of the foundations of everything. And I think that this will give us very, very important answers, or at least tell us also what are the right questions to ask. Because the goal of research is not just to discover new particles, it's also to understand if the questions we are asking ourselves are the right questions to ask, or we have to change direction. So, for sure, a collider like the FCC will allow us to make a big step forward in our understanding of the universe.
So I think that we actually run out of the time, and this was actually I think the great question and the great answer to finish this. So I would like to thank again both of you, to Fabiola and Charlotte, for coming to Ostrava and sharing everything with us. So thanks again.